Welcome PCS members and friends to our PCS IBS seminar. We are very happy today to host at our seminar Dr. Rose Davies for the second time in a few weeks from Aston University in Birmingham. And our scientific host today is Sergey. And I don't know if we need another brief introduction.
Yeah, thanks and welcome everyone. Maybe we can keep this brief. First of all, because it's shortly before we are running into the next New Year celebration, now the Asian New Year celebration. And that's also why there are already some people who are not anymore in the audience. But it's great that there are still so many who are in the audience. So we had already a talk by Rose 2 weeks, I think, ago, and the idea was just to listen to one more topic, which was part of your, I think, PhD work on Coulomb blockade in a non-thermalized quantum dot. And I think we just proceed without further introduction. Thank you very much for being with us. Thank you for agreeing to give a second talk. Let's welcome the speaker.
Thank you, everyone. Yeah, thanks for inviting me back for a second talk. So, and yeah, we'll try to keep this brief. You know, everyone wants to go and enjoy their weekend. So, yeah, this work was done with Igor Jokovic, Igor Lerner, and George McArdle. And this was actually work that I did in last year, which led in essentially because you'll see from the similarities to my talk last time of why I got called in to help out on this project. Structure of what we're going to talk about today, I'm going to give a very brief introduction to quantum dots. Specifically, we're going to talk about what thermalization of the excitations means and what it means for a non-thermalized quantum dot. Then we're going to talk about the Coulomb blockade regime, essentially answering both parts in the title, and specifically the Coulomb staircase as a signature of this Coulomb blockade regime. Then we'll introduce the model that we used, which was a resonance leveling model, for which we'll use to derive this current formula quickly, and also have a quantum kinetic equation. We'll then solve this equation to get the probabilities of having n particles on the dot, to then find the conductance. So that's the plan for this next hour. Okay, so I'm sure most of us are very familiar, but quantum dots are essentially electronic systems where you can combine them in all three spatial dimensions. So it's a sort of puddle of electrons that are all combined. It's the true particle in a box. And the ones I'm interested in are ones where you can connect them up to leads. So unlike some of the optical stuff where you just kind of pop them in a lattice and shine light on them, I'm very much looking at flowing current through them. So here are two ways in which you can fabricate them. So again, using a two-dimensional electron gas, much like I talked about with quantum point contacts, you essentially want the electrons to flow from your source to your drain, and there's some top gates that sort of isolate a central region. Or you can do it on a nanowire stave and directly do it on a 1D system. And this is just quite nice because you can really see the fine fingers and how small the control is. This is for a triple quantum dot, but the idea is the same. So when we talk about quantum dots, there's a lot of parameter regimes. And so I just thought I'd throw them all up on the board and start writing. So, because we're going to talk a lot about different regimes. So here we have some mu R, mu L, chemical potential of the leads, and we'll have some energy levels in the dot with an average spacing delta. We have a temperature that couples uniformly to the entire system. The charging energy, the energy to add an electron to the system. We also have the Davies energy, which is related to the time taken to travel across the system. We have the number of particles on the dot. It's not always a good quantum number, but for Coulomb blockade, which we'll be considering, it's useful. So we have n particles on the dot. And then finally, we have our thermalization rate. So This is if a particle hops on, how long does it take for it to thermalize down to a sort of lower available level? And we also have the coupling to the leads. So gamma R and gamma L. Okay. Lots of energy scales to consider, and also the side gate voltage, which essentially considers the chemical potential inside the dot.
When you draw these levels, the spacing between them, is that already taken into account the Coulomb energy, or is that the non-interacting?
That is the uninteracting.
That's the non-interacting.
Non-interacting picture. Yes. I could draw it a bit better if I was doing it like that. Yeah, we'll see. So the first thing to talk about is the thermalization rate in quantum dots. And so for a zero-dimensional diffusive quantum dot, the thermalization rate is given by this formula, which is found by Saban, Imre, and Aronoff. When I say diffusive, I mean diffusive from scattering from the boundary of the dot, not due to impurities, because we're more interested in a very large Thermalise energy, essentially, in our case. So G is dimensional conductance in this formula. This formula is only valid for this energy range. The first thing to note is that in this, if we just substitute in the maximum of this, we'll just get gamma is equal to delta, but gamma is less than delta. For any epsilon in this range, it will be smaller than delta. Okay, and so as we consider a large dimensionless conductance, essentially the range in which this formula holds is going to get larger, and gamma will always be less than delta in this regime. Epsilon, I think I said, but it's the quasi-particle energy. And in general, it's going to be related to the temperature or the voltage difference between our biased sides. So essentially, if we want to consider a system that has gamma less than delta, we're going to have temperature being larger than gamma, right? Otherwise, our quasi-particle energies are not going to be within this range. And importantly, for our system to be non-thermalizing, we need gamma to be much, much less than gamma. So we need the rate at which the system is thermalizing to be shorter than the rate at which it's tunneling onto the system. So it tunnels onto the system, doesn't have time to thermalize, and tunnels off the system. In this case, we can call the system a non-thermalizing quantum dot. I guess one reason is why do people care about this? Non-thermalizing cases are very interesting because they really show there's lots of work on non-thermalizing cases, but below this regime, the question is what happens to quasi-particles energies below this? And for this, that's when Fermi's golden rule no longer holds, and we have to consider a slightly different picture, but this was done by Alshuler, Geffen, Chambev, and Levitov.
A question, is it related over the thermalization and imaginary circulation?
Sorry, it's the...
Is there any relation between the thermalization and in the impurity model concept in self-energy, imaginary self-energy?
I'm sure that if you did some sort of expansion you had some sort of, it's all to do with the, let's see, C dagger, C dagger, C sort of interaction term, right? So there is probably some expansion that you can do. I don't know the details, but I'm sure that there is some self-energy that is related to this. Here, this is essentially a quantum dot undergoes a delocalization transition below critical energy. And the way to see this is that an excitation of the quantum dot will break down due to electron-electron interactions into particle-hole pairs, particle-hole pair, and another particle at different energy. And so we can essentially view this as forming like a Cayley tree of different possibilities of routes to go down when a particle is at a specific energy. And the authors here essentially showed that there is a transition between a localized state where it's localized in Fock space to a delocalized state where it explores all these possibilities. So essentially, there's an energy range at which there's localization in Fock space. So quantum dots are an interesting system because we have a localization in Fock space, similar to how MBL also has localization in Fock space. Obviously, there's differences between this and MBL. This was discovered first. I'm sure everyone's probably familiar with this. But we're in a very interesting regime that we're looking in, where we're non-thermalizing, but we haven't quite hit this localization transition yet. So quasi-particles are still a good description of what's happening. So we're not quite here, but we're still in this non-thermalizing regime that's approaching this. Because this work was done not really considering the gammas. Anyway.
Sorry, question there. To please clarify the meaning of the localization, the quasi-particle in a quantum that sounds like already confined in space.
Oh, sorry. Yeah, this is Fock space localization.
In Fock space.
So this means that an excitation of the system does not decay into multiple particle hole pairs.
I see. You mean and not sensitive to the temperature?
Not sensitive to the temperature. Yes, because the localized state must also not be thermalizing, right? So there's also we haven't got to that point. Actually, no, we did. I was saying that we're considering a large dimensionless conductance, which means that we're away from Anderson localization. So we're not worrying about that issue here because we're at a large dimensionless conductance. But there's this other strange thing that happens, which is this localization in Fock space. But this is just to set up why we care about this regime and why we're going to investigate this regime. Yeah.
It seems, I don't quite get it, but it seems that in the localized regime, one quasi-particle, one electron excitation can produce infinitely large amount of particle hole pairs, but each of them should cost at least the delta of energy. How this can be? Because the original excitation has some energy above like Fermi energy, and then it can create, I don't know, 5, 10 pairs. But
yeah, so this is the thing that these authors did, which they showed that actually there's like the coupling to the next generation decreases as you go down.
Okay.
So yes, you're right. In this sort of delocalized case, which is what we'll kind of be considering, but in this delocalized case, an infinite ones do appear. But there's this localized case in which the coupling decreases as you go down generations. That's what these strong lines versus dotted lines. But this is, again, to give you inspiration for why we're talking about this.
But localized here means that your Fock states are good approximations to the true eigenstates, right? They're almost the true eigenstates, which means you are basically close to non-interacting. That's the non-interacting picture, because the Fock states, I guess, are the product states of single particle states, aren't they? So that localization regime actually corresponds to weakly interacting charges, while the delocalized regime, therefore, by this logic, must correspond to strongly interacting charges over time.
Yes, right.
You're correct. Yeah?
I think so, because it's especially to do with this sort of, and it happens below this energy. So as your energy decreases, i.e., how hot the electron is that comes on.
What happens below? So below this energy, you are in this localized.
Yes, above it.
And above it, the interaction is important.
And the part that we care about is sort of, we want to be above this, but we want our thermalization on the dot rate to be
in the delocalized regime.
Essentially, but with.
So that you can trickle down, but without thermalizing.
Without thermalizing, yes. Okay, so now we're going to talk about the Coulomb blockade, which should be a little more. I call it classical. I'll explain why in a second. This Coulomb blockade regime is defined by this separation of scales. So Charging energy is the most important and the largest scale in our system. Costs a lot of energy to get an electron onto the dot. Here we have our individual single particle energy level spacings are renormalized by the coupling to the leads, but only by a little bit. So they all renormalize separately. And then this is then smeared out by a temperature. Again, we want this temperature so that we can have our delocalized view. So for this, you really see the effects of charge, like an individual charge, because it costs a lot of energy for one single charge to hop on. I say classical and quantum, these are in heavy quotation marks, because there's a regime that lots of people also look at is swapping these two round. That's when there's sort of two types of discreteness in the system. There's the discreteness from having n particles and n+1 particles, and there's the discreteness between having different energy levels in those subspaces.
Can you comment experimentally this much greater than, does this mean like a factor of 10 or 100,000 or?
I'd have to go back to the specific calculations we did. I think it's somewhere between 10 and 1,000. It's not massive, it's not small.
Okay.
It's enough. But in this regime, what's very nice is that there is a Hamiltonian that describes exactly what's going on. This Hamiltonian is just sum over single particle energy states, and we have our number operator here, and our Ng, which is our gate voltage here, and EC, charging energy. So this is a review that goes through why this Hamiltonian effectively describes this problem. So two of the main features, well, first main feature of the Coulomb blockade regime are these peaks in the conductance when the gate voltage is changed. So the reason why we have these peaks is because the energy to add another electron onto the dot is given by this. This is the energy of having n particles on the dot, and therefore the difference in energies is given by this omega n. So if we set Ng to be a curly n over here, that means the preferred state of the dot is to have this curly n number of electrons. And here we see the difference is going to be of order EC, and nothing can tunnel on. There is no available states because of this strong charging energy. However, as you shift the gate voltage, that essentially moves all these states across and makes it such that the n, curly n state and curly n+1 substates are at the same, at resonance, and essentially a particle can pop on. So this amounts to sort of changing the chemical potential on the dot such that this is the case.
And the charging energy depend on the Ng, right?
The charging energy is independent of Ng.
No, depend on the Ng. Because with more charge on the dot, it can be like harder to.
Yeah. That is very true. We're considering quite a large number of particles on the dot, so it's not so important for what we're interested in. But yes, you're right. For smaller dots, that would definitely be a factor. The other important regime feature is the Coulomb staircase. Essentially arises from the exact same ideas, but instead of changing the gate voltage, we change the source drain bias. So here you see a sort of better description of these different n particle subspaces with different energy deltas, and at a sort of linear conductance, nothing can happen. But then we increase the bias, and then suddenly there's enough energy to hop on to the system, and you end up with these classic steps. So what previous theoretical work has done is that they've often looked at the master equation. And this master equation, they essentially, although they put in different thermalizations, you essentially assume that the distribution on the dot is given by a Fermi function. That's how they solved a lot of these problems. And what we're going to do is not assume that. We're going to do a fully quantum calculation. Now, I also want
Sorry,
to say,
the Altschuler, Geffen and so on paper on this localization versus delocalization, of course, also doesn't treat any thermalization. I mean,
Yeah.
they just look at the Hamiltonian isolated problem.
there's one thing to say about this, which is that lots of people have done fully open quantum dot Lindblad equations on this system. However, due to the way that the technique works, they've often looked at the case where there's not many particles on the dot. So there's 3 or 4 states, because then we have quite a small state space in which to consider. But we're actually looking at this thermally broadened case where there's a continuum of states on the dot. So this is why essentially our paper that we published, sort of caught something that lots of people had missed in the Coulomb blockade, which I think everyone basically thought there was nothing more to say 15 years ago. But we managed to see that actually, if you treat this in a non-thermalized way, there's a unique signature in the conductance that will tell you whether your quantum dot is thermalizing or not thermalizing. So this is useful for anyone who wants to experimentally investigate this non-thermalizing regime, because you can just look if your system has this extra peak in the conductance. And if it does, we're non-thermalizing. And if it doesn't, then we're not. Okay, so let's start talking about this model. Here, what we're going to do is that we start with a Hamiltonian. So we start with our Coulomb blockade Hamiltonian leads that connect up to reservoirs, and the connection between the tunneling is different from from my previous talk, where we considered only coupling to the ends of a wire. Here, this coupling is uniform on every single state. This is basically the resonant tunneling condition. It sort of makes more sense in energy space, which we'll see in a couple of slides, but this is really an important choice. And we choose this hierarchy of scales, which I talked about. So we want a non-thermalizing dot. And the fact that it's non-thermalizing means that we can use this equation without having to change anything, right? We don't have to worry about how it decays down. So we need an expression for the current in the reservoir. What we do is we use the Mayer-Wing-Green approach for non-equilibrium Green's functions.
Can you go to the previous slide?
Yeah.
So En here is the energy of the state in the dot. Do you consider also the interaction normalized of this, or you only say that you have the delta only?
So sorry, you say that.
No, I mean the E.
Oh, this one. Yeah.
So this one you say that is only depend on delta, or you also add the interaction in terms of
So yeah, we just say that this is only delta approximate, because we're going to use the thermal smearing of all the states anyway. And we're considering this very large Coulomb blockade regime. So essentially we assume that there are some states. Yeah. Exactly that. We're only going to assume delta. All electronic interactions is encapsulated by this Coulomb blockade that we'll consider. So yes, we'll consider the current in the alpha reservoir, and this is going to be given by the time derivative of the number of particles in the alpha reservoir. If we calculate this commutator, we end up with this expression, which is the real part of this Green's function. This Green's function is a combination of creation and annihilation operators in the leads and the dots. So there's N and K alpha in the indices. We can then do an equation of motion on this Green's function to then find this expression. Essentially, what this does is that we've written our Green's function in terms of n and k alpha, in terms of the product of G, N, M. So that's two operators on the dot only, and two operators on the lead. So essentially you can decouple them because it's linear in the leads. We'll also consider the time-ordered version. The time-ordered version, and it's on the Keldysh contour because we're doing non-equilibrium. We can then analytically continue this and use current conservation to get this expression for the current. This is all very standard techniques. And the thing that's essentially very nice is that we don't have to worry about any matrix issues because we assumed this uniform coupling. So it just means that this doesn't have any traces in compared to what I talked about last time. Okay, so we have our expression. Now we need to calculate what the Green's functions are.
Sorry, in the previous slide, some single particle levels of the quantum that let me know where is this information in your
So where is
the single particle levels?
Single particle levels? Well, that's included. Yeah, I guess we'll see it in the next slide, but there's some trace over all the single particle levels in this Green's function.
I see the dimension of G.
Yes. Because yeah, G here is the particle Green's function for on the dot, and it's going to depend on your n indices, and we're then going to sum over all of those.
Thanks.
Okay.
So,
Yeah.
alpha is either left or right.
Yes.
And so in the right hand side, this G, small little g that you're writing, which is alpha independent. What is that?
That should 100% have an alpha in. You are very correct. Just seeing it now. Yes, that should definitely have an alpha. The reason there's no alphas here is essentially you use current conservation to write current on the left and the current on the right, and then you take a similar symmetrical combination of them. Thanks. Yeah, no, that's very right. That should be an alpha in there. Okay. For the isolated quantum dots, we can write the Green's function. So here, we're going to show that the Green's functions are sums over the n particle subspaces. So this is our isolated Green's function. It's equal to, as you pointed out, the sum over all these GNs, and these GNs are given by these formulas. So it's the trace over all states for subscript n. So this is all quite standard. What we'll then do is that we will transform this to an energy picture. Particle number is conserved in the isolated system. So we can rewrite our problem in terms of the smaller, well, G capital N, where this is the trace over the n particle subspaces. So essentially, we've split up our big integrals into sums over all the n particle subspaces. And here we have our two delta functions ensuring energy conservation. So the reason why we have different omega n's here is because, note that in this one, we act the creation operator first. So that takes us from an n state to an n+1 state. Here, we act the annihilation operator first. That goes from an n state to an n-1 state. Those can have different energies in general. That's why this term has this that enforces energy conservation, and this has this n-1 that enforces energy conservation.
And you put on the temperature, go to row naught.
Yes. Our temperature is basically all in here. Okay, so we have a new description for our isolated Green's functions. Now we can write our quantum kinetic equation, which is given to lowest order by this expression.
And so basically you assume that because of the traveling energy is very big, you can only allow one particle to come in and come out. You do not allow two, right?
Yes, exactly that.
Sorry, the condition you mentioned also valid for the particular value of Ng.
Yes. So the Ng, although this condition is valid, what we'll end up doing shortly is that we always make sure that only two N particle subspaces are relevant. It doesn't really matter which ones they are, but we just know that it is two states that are relevant. The N and the N plus one, or N plus one and N plus two, whatever the corresponding Ng would be.
But in this case, do you consider some scheme of the Ng is a half integer or Ng become integer? So you have the plot before that the curly N can be integer or half integer. So the state that available will be different, right?
Yeah, so we'll see what we'll end up doing is exactly like you said, that we have these states here of the different energies that are possible. What we're really, this procedure works for all of them. I think this procedure works in general, but what we're really going to focus on is when only two states are relevant. So this is, that's actually okay, because also we're going to be increasing the bias on one side. But essentially, we only want two states to be relevant. And as you said, depending on your Ng, our sort of voltage range over which this is true will change. So in this case, we often will assume that omega n is equal to 0.5 EC. Essentially means that we're considering it's in the ground state, and then you add a certain amount of voltage, and then you get to this one that becomes available. So yes, exactly that. Yes, so this is our resonant tunneling. The crucial thing, and why I think the resonant tunneling thing is important, and those assumptions that we did earlier, is that this is all happens at the same energy, and notice that it happens for the same n, subscript n. So this truly is your particle hops on for an n and also hops off at the same n. This is a non-thermalizing system that if we were to consider a thermalizing, this state probably won't be true anymore. But we're really considering that it hops on and hops off at the same energy. So what we can do, plug this in. Hopefully we have, yes. So what we're essentially going to do, I'm noticing the time, we're going to rewrite this ansatz as this, the pseudo equilibrium form, where Fn is the energy distribution to have n particles, but for the n particle states. Okay, so what this does, here's our nice equation that we finally got to. This is our quantum kinetic equation, and it's got a very nice interpretation, because this is the probability of having n plus 1 particles. This is the probability that the n plus 1 particle state is occupied. This is the probability that the state of the leads are not occupied. And same on this side, probability of that we have n particles in the system, probability that this state is not occupied, and the probability that the corresponding state in the leads is occupied, right? So this is our equation that we're going to solve. And there's the normalization conditions. Sum of all the probabilities has to be equal to 1. And there are n particles on the dot, essentially.
So you assume it's a lead equilibrium, but the dot is not, right?
Yes, the leads are at equilibrium, sorry. Okay. Oh yeah, one final bit. The results for thermalization can be obtained by summing over this equation and replacing Fn with our F, the Fermi function for some chemical potential. This essentially completely reproduces the results of Wiener. That is the equation that he got.
So what is the temperature in this in the upper equation?
The temperatures,
the
the temperatures are basically all contained within the Fermi functions of the leads. So yeah. And just a quick note that this procedure I think might not work for noise, which is what I'm working on now, because of this, what I said about the resonant levels. However, for thermalization, everyone did the master equation. We can see that it works exactly. It just reproduces every single result that people got from the master equation. Okay.
Sorry, so
Yeah.
N is the probability of having N electrons on the dot.
Probability of there being n electrons on the dot. If you want, essentially where it comes from is if we took the trace of rho naught. Essentially it comes from this bit.
Then the temperature dependent.
Huh?
Then the temperature dependent.
Yes,
Yeah.
it's going to be temperature and related to lots of other parameters in our system. Because so e to the beta h EC n squared n minus ng squared over 2. Because this trace was over the n particle subspace. So we know that this term in the Hamiltonian is always there. And this term is related to the probability of there being n particles on it.
And this beta is the temperature of what?
The entire system. We're considering it's in thermal equilibrium everywhere, but in biased.
I see. But since you stressed it earlier, your quantum dot is not in equilibrium, right? So there cannot be a temperature there. You are not in the thermal region. So
Yeah, I mean, we're not in the thermal region, but we're assuming that there is some heat bath somewhere that it couples to, which is in some T.
heat bath coupling to what?
The
The whole
The
system.
whole system, I guess. So we're just really assuming that everywhere is in some temperature.
And this is the same. So you're also assuming that the left and right leads also have this particular temperature, or they
Yes.
have different.
Yes, that particular temperature. All the non-equilibrium features come from will be showed in this distribution that will end up with.
Showed in distribution of EM.
FM.
And do you mind what FM?
Yes, FM is essentially this. It's the probability of a given state in the n particle subspace being occupied.
You are assuming.
The ground, right? How the Theorem will keep the matrix and do an average. What? How to average?
But we haven't, there's, this was for some Gn, so we haven't taken the average over all n levels yet, but we do at some point.
Or average, or partial state.
Yes, the average over all little n's. Yes. But this is with the restriction that we're in n particle subspace. Okay, so
So there is another additional assumption that your quantum dot has some sort of a Gibbs distribution. Is it not? Otherwise, you cannot write the rho naught in that form, it will be minus beta H.
I think so. I think we're making that assumption then. We're definitely assuming that it's thermally weighted like this. Yes. Okay, so we'll just about be okay for time. So I want to show one thing, which is that, and this is also helpful if I write some examples down, because the equations are kind of gross. We're going to solve this equation. Now, this equation in full is recursive for every single capital N, right? But we're going to make this assumption that only two states are relevant. And if we're at a very large charging energy, and exactly like what was pointed out, we have to just make sure our voltages and everything are such that we only have two particles that are two N particle states that are relevant. Okay, so this is the solution to that equation, and it's the exact solution. Okay, it's very hard to pass at the first time. So we're going to start with this. So this function here is defined as the multiplication of all these phi's, where phi's are related to our F tildes that we introduced earlier. What this Zn is, so if we considered a state that only had three energy levels, epsilon 1, epsilon 2, epsilon 3, Z2 is related to all the ways of putting two electrons in the system. Right? And then what you do is you multiply all these phi's. So we have, this is equal to phi E1, phi E2, plus, phi E2 plus omega n, phi 3 plus omega n, dot, 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 dot. So you see that what this Zn is that it's the combination of every way to fill up these states. Okay? What the delta function does is that it enforces the fact that we only have n particles. Zn plus 1 is making sure we only have n plus 1 particles. But this is making sure that we're taking all possible ways of occupying all these different EJ states. Okay? Then the final thing is that Zn En is equal to the same idea, but with the restriction that E2 must be occupied, for example. So in that case, you take out this probability here. Oops, I didn't write the problem. Okay. So we have to make sure that E2 is occupied. Okay, so the reason why this works is you can plug it into your quantum kinetic equation, you can get this, and you get this thing out just by plugging that solution in. Now what this solution says, every single way of writing n particles, every single way of distributing them, minus every single way of distributing n particles such that En is occupied. So that together makes every way of distributing n particles such that En is not occupied. And we then multiply it by this term, which then gives us every single way of distributing n plus 1 particles such that En is occupied. Okay, so this is why that ridiculous solution works. I think it came to Igor Yerkovich in a dream. It's a bizarre one, but it is an exact solution when there are only two states. And I'll save you the pain of going through the rest of it. Essentially, we show that Fn is equal to Fn plus 1 for large n. pretty self-explanatory result, but I did want to at least show the full solution. It's kind of neat. Okay, so we can then rearrange. We get Fn in terms of these. So this is now, if we rearrange our quantum kinetic equation, this is what we get, the An being the ratio of probabilities. We can then split up our F tilde into 3 regions. And it's sort of like, well, we can split up our Fm into different regions because F tilde is just related to FL plus FR with some gammas. Right? So no wonder there's 3 regions. One region is when both Fermi functions are contributing. One region is when one of them is. The other region is when both of them are. So we can use this to split up our Fermi function. Here we go. We essentially get this. The normalization condition is split up into this transcendental equation. Okay, so we now have all the ingredients, finally. And all the ingredients mean that we have a distribution, we have a transcendental equation to solve to find out the ratio of probabilities.
So could you go back to my question? So your probabilities appear where exactly? In the transcendental.
Yes, yeah. And it's the ratio of probabilities.
So Pn over Pn plus 1.
Other way around, but
Okay. And what is EF?
EF is related to the Fermi energy on the dot. It's essentially M delta. That's what it's related to.
And so this equation has solution for any beta?
Well, I mean, I'm pretty sure this equation does have solutions. We managed to find. We tried to solve it and there are solutions. But we do have to obey the parameter range that we set out at the beginning of the problem, which is actually quite restrictive.
Otherwise, you need to.
Human beta. Yeah, that's for sure.
Yeah, the beta is kind of fine this term because this term is related to EC and EC is larger than temperature, so it's not kind of basically. Yeah, and I mean there are solutions. Okay, we can get some results. So for symmetric coupling, we get this for the probabilities. It matches exactly up to master equation and the thermalized result, which is maybe to be expected, but if we look at Pn here, so this is the probability that we're have n particles on the dot. It's 0 until we increase our bias up to a certain amount, essentially half EC, and then suddenly it decreases. And then here is where our results are no longer valid because you then have to consider the n+2 state, which we can't.
So yeah, just to understand the comparison. So master equation solutions, as you mentioned earlier, cannot be. So you are considering some sort of linear equation.
No, this is not the Limblad. This is like I forgot the name, but it's just the one using distributions and rates rather than any jump operators.
Okay. And so do you still have the restriction that you cannot consider too many electrons?
No, not with that one, because they don't solve the distribution directly, because they assume that it thermalizes. So they assume that if you hop in, they assume that the distribution in here is always given by a Fermi function for some mu dot.
I see.
So they assume instantaneous thermalization. whereas we're assuming the complete opposite case of no thermalization whatsoever.
Well, you have a temperature.
I think when I say thermalization, I mean specifically hot electrons are not thermalizing down
In the dot.
in the dot. So yeah, this is completely the same, but that's okay. All of our interest is related to the fact that we have a double step distribution function. When you just plug those probabilities into what we got, you end up with these three regions. So we have essentially the Fermi, it's one, all these states up to this are occupied, and up to the higher edge are occupied with a reduced probability, and then 0. So just to, again, make this clear. The thermalized case is just a Fermi function, right? A Fermi function up to where our bias is. Our case, what happens is as soon as V is larger than, as soon as there's enough energy to put an electron on there, i.e. AN is not 0, then what happens is this sort of shelf develops. And the size of the shelf is related to how much voltage above our omega n that we have. So we just get this weird double step distribution function. And it's a feature of this non-thermalized case.
Sorry, the question, what happens if the voltage you apply is negative?
Well,
Left to right, then right to
Yeah.
left.
you can essentially swap all these results. But you again have to be careful to make sure that only these two n states are possible. But we calculated this with, we mostly used asymmetric biasing, but if you use symmetric biasing or on the other side, the results still hold, but the current is.
So this the voltage is the difference between the leads and not the gain you apply to the quantum dot.
Yes, it's the difference between
I
these.
see.
So yeah, this is the very interesting thing, that we get this weird step that develops.
I have a question. In your calculation, how to treat of the spin part?
The
You
spin part.
consider the
Yeah.
two
So
level and average the up and down state.
yes, so one of the, I guess, unfortunate things about the Coulomb blockade Hamiltonian that we use is that it doesn't really consider spins
But the
interactions.
electrons in the lead.
Yes, because as soon as you start considering spins, we'd have to deal with condo. It's essentially why we don't consider spins. Okay. These double step functions have actually been seen before, and they've been seen in 1D systems. So this was an experiment done by Potier, and they saw this sort of non-equilibrium double step distribution. So that's quite interesting that you can get this double step distribution. You can't measure it in a quantum dot, though, specifically, so we have to look for signatures of it elsewhere. And the signature that we found is there is this nice extra step that happens. So here, this is the conductance. The dotted line is the 0 temperature thermalizing case. When I say thermalizing, I mean essentially the distribution on the dot is given by a Fermi function. And here you see that we change our parameters to get closer and closer, where EC gets larger and larger. And you see what happens is that we recover this first peak. The difference is to do with the 0 temperature limit, but we have a distinct jump that happens here, right when B is equal to EC. This jump kind of gets smeared by temperature. It still kind of goes the same amount, but it jumps earlier. So the jump is a bit smaller at finite temperatures. And this is basically the main result that we say, if you want to know whether your dot is thermalizing or not thermalizing, then we have to ask, is there a jump in your nonlinear bias at EC? So if there is, then that indicates that your system is in a non-thermalizing regime. And if we know that, you can then explore further questions about this regime. I'm going to say one more thing before we finish the time, just because I want to explain where in the maths this jump comes from. So this is just the current formula, but the important thing to note here is these integral limits. So we have one that goes from omega n minus 1, the EB above that, omega n, and omega n plus 1. If we look at our distribution function, essentially it looks like this. This is very large because we're assuming we're far away from the bottom of the dot. Omega n and n plus b is this range here. It's related to the size of this set. Omega n plus 1, omega n plus 1 plus EB is related to this regime here. And we have the same thing here. It's omega n minus 1. So what happens as we increase EB is that these windows essentially extend. Right? These windows and this term extends. And when we're at EC, it turns out that these cross these boundaries and then start to contribute to the current. So when we increase our bias enough, this double step function has an extra step that corresponds to when these terms start contributing to your intervals. So this is why this step appears, and it's very strange. We don't really have a good heuristic explanation for why they are there, but they certainly are, if you do the maths. And they disappear if the coupling to the leads is asymmetric. So as you increase the asymmetry of the leads, you see that this slowly disappears.
And so what's the gate voltage in this case? That's integer, around integer value.
The gate voltage is such that omega n is equal to 0.5, which corresponds to
So not in resonance. It's not in resonance.
no. Yeah, it's not in resonance because it starts off with 0 until we increase the
Yeah,
voltage.
but do you have such behaviors if you have the conductance dependence on the gate voltage?
Yeah, everything just shifts. The entire behavior essentially just shifts to and from, because it's always here where we can't do get any further, and shifting the gate voltage essentially moves where this starts. So this is only the first step, and you can't really do anything. But yes, so here we go. The whole point of this is that absence and thermalization in a quantum dot can be experimentally seen through looking at its non-linear conductance. And you should expect a jump at this point. And the next things to look at is whether there are any unique features in shot noise and higher moments. This is exactly what I'm working on right now. And yes, so that's it for me. Thank you so much for having me again, and enjoy the holidays.
Okay, more questions? Yes, please.
So, to explain this resonant tunneling condition some slides ago in terms of the Green's function, and then you explained again those in terms of the probabilities, in terms of the relation that you derive using the exact solution that related F and Z, if I remember correctly. So further back. Yeah, this relation, how do I understand this relation heuristically? The probability relation, I sort of understand.
Press plus, Rose. Down on the right.
Thank you. The way to see it is exactly that what the Green's function is doing and what this is essentially putting in is that this is relating the energy at a given, for a given n, we are considering a specific En that's in the dot. This is then getting coupled to, at the same energy, a part in the leads. So it just means that we are coupling exactly to leads at one energy. So this can pop in, pop off. That's exactly what this rising tunnel condition means. It's mostly been used, this condition, in sort of Anderson type problems, where you only consider sort of one, within a sort of two-level systems. But here we're using it for every single level. So what that means is that if you consider EM, that's then only coupling to the levels at the exact same energy. Because the system is not thermalizing. Whereas again, when I say thermalizing, I mean this state is not related to this state at all.
More questions? I have one. So this was, as you explained, assuming that you are in this strongly interacting regime of the Altschul-Geffen quantum dot pictures that we see in the non-local. What happens if you reduce the interaction and you come into this so-called localizing regime where Fock states are good atoms? What happens there? What happens to your curves?
I have zero idea what would happen, because the problem is that for this state, these states to happen are essentially quasi-particle picture will break down.
Say it again.
Well, it's that the quasi-particle picture, when we go right back to the start.
Well, it's the other way around. In the localized regime, the quasi-particle picture should be a good picture, isn't it? I mean, because it's essentially a non-interacting system. The funny thing is this delocalization due to strong interaction with some delocalize on what you call the KD tree, actually, yeah. So which means that all your Fock states are not anymore good eigenstates.
I don't know. I need to think about that. What actually would happen at decreased energies? Because I think
well, maybe I'll ask another bit. So what are the Fock states? What do you call Fock? Can you show this picture again? Localization? Yeah. So what are these red things there? What's the Fock state?
Fock states are related to the excited states. So the first state is just an excited state of the system. I would have to re-go through this paper because I haven't re-looked at it in a while.
Let me re-ask. So are these product states of non-interacting single particles?
I'm pretty sure they should be single particles.
Then I think localization means that your Fock states are almost good eigenstates. Approximation.
I think so. I think that the main difference is this tunneling.
They're still non-interacting picture. Non-interacting picture is a good picture. So then I thought always that's what I would call good quasi-particles. Well, when I have strong interaction and it breaks down, then I will say this is something I don't know. Yeah.
I think essentially. Okay, let's think exactly what I mean by this. The thermalization rate for a specific energy, to get a good quasi-particle, it has to be much less than that energy. That's the line that they definitely wrote.
I
similar to the you calculate the green function.
Mhm.
Based on the green function, you can calculate the spectral function.
Mhm.
Right? And spectral function in thermalization is more very similar to the level 3. Level spectral function is a delta function like level. But in summarization, this is very straight. And you check that this kind of difference between the spectral function of spectral function in summarized limit and non-summarized limit. This is
So yeah,
example directly.
The spectral function in what these two regimes.
Yeah, for example, is local D Dega D
Mhm.
or D Dega C or some. You can many kind of spectral function, right?
Mhm.
And this spectral function is a good way to compare the single particle picture in anybody system. So you can compare the different summarization, and you can calculate the what one looks like the spectral function is a good way to compare.
I'd have to think, but I think the deceptive thing about this is really that they're not considering current through this system. That is inherently why what I went on to talk about is slightly different from this specific examples. Because these examples are considering infinite isolated 1D system. What you're saying about checking the spectrum
Of the different imaginary part of green function.
Yeah, because the imaginary part of the Green's function is just related, in our case, to this broadening. And we always say that the broadening is small, such that you can still imagine all this broadening happening to each individual energy level, and then we thermally broaden them. So, I mean, I think it should be. I think it's okay. Yeah. So, I hope it's okay. But it's definitely for our given parameter range. We've checked with the systems that we're interested in. We've checked the hierarchy of scales that we actually want, and we are in the regime that we are talking about. You can get to that regime. I don't know what happens outside of the regime that we've looked into yet.
Okay, more questions? Well, if that's not the case, then let's thank Rose. Thank you very much. And we wish everyone Happy New Year. Enjoy your rice cakes or whatever will be on your menu. And I think